All right, while we are waiting, you may better take out your book and take out your calculator as well. Okay, it's time to. Today we would like to do some more calculation. Your calculator piece, or maybe your sheets. Okay, because we need to time on doing some calculations in chemistry. Now, just double check if all of you are here. One more guy missing. Who? There should be one more guy. Oh, we've got 26 only today. And let me see. Yeah, just 26. There should be 27. Yeah. Perfect. Now, before it starts, I remind all of you to take out your book, and most importantly is your calculator. Okay, and we need to deal with so many calculations today. Okay, are you ready? Now, before we start, I would like to remind you about the Chem Quest. Chem Quest will be scheduled on this Friday. You still remember, you know what? This Friday, on which topic? On which topic? Phong Ai?
Rusting, is it? In the
I have just shown it on your Google Classroom to tell you the announcement. Do you realize it? Tân Ho John.
Hi. Reactivity of metal.
Yeah, reactivity of metal this Friday. Well, next Friday is rusting. Okay, thank you. So this is what I would like to remind all of you. And today, we are going to have to start a new topic on calculations in chemistry. So remember, it's just episode 1. We have got episode 2, episode 3, episode 4 in the coming years. So we would today we try to tell you how to count something in chemistry. But wait a minute, Mr. Chin, how would you count it? Well, you may find it counting in chemistry is rather difficult. It's quite different from like this x. If you like to count x, we call it 1 dozen, which means 12 pieces. But in chemistry, 1 dozen, that number may be you just count it as about will be too little. Indeed, in chemistry, we would like to count the atoms, ions, electrons. Okay, it's up to us whether or not it can be so many, right? Ions, it can be electrons, etc., and molecules. And you would love to calculate as a larger number. We call that 1 mole, mole. So what is that? And 1 mole. And that number comes from one chemical. We call it carbon 12. Okay, just remember carbon 12. And in one meeting, those scientists come up with that number. It is defined as the 12.00000 gram of carbon-12, and they want to tell you what is meant by 1 mole is that the number of the atoms found inside 12.00000 grams of carbon-12, they will contain that number. We will call that number 1 mole. Okay, but what is that 1 mole? 1 mole, we have got an exact number, 6.02 times 10 to the power 23. Okay, so if I put the word per mole here, per mole, we will say this one, we call that Avogadro's constant, Avogadro loss ratio. So we try to be referenced with this number, okay, from today onwards. Okay, first of all, 1 mole, just like 1 dozen while you're having in daily life. Okay, but 1 mole is quite different from 1 dozen in terms of the number. The number is very, very large. Okay, how large is it? 6.02 times 10 to the power 23. So many zeros there, right? So many zeros. While that number comes from the same number of carbon atoms in 12. Now I would like to mention again 12.00000 gram of carbon-12. Okay, remember carbon we have got different isotopes, just like carbon-13, carbon-14, but you just throw them away. We focus on carbon-12 only. Okay, so that number is very, very large. Do you understand? So this is what I would like to talk to you here. And remember, starting from today, we will focus on some terms. For example, can I say that we have got 1 mole of chlorine? Now, if I say 1 mole chlorine, that may be something ambiguous. Okay, it can refer to 1 mole of chlorine molecules, or it can refer to 1 mole of chlorine atoms. So whenever you see the questions, please be aware of the term atoms, molecules, ions, etc. You understand? So let me put it this way. I'll give you one more example. For example, 1 mole of chlorine gas. What is mean by that? How many chlorine atoms are there? How many moles? Okay. 2. Why?
2. Because chlorine exists in a CO2 molecule in gas form.
Yeah, chlorine gas means chlorine molecules. Okay, will exist as diatomic molecules. So the formula, they will tell you they work in pairs. That is Cl2 molecules. So the similar concept that you may know about this, and you may find that here comes what? Because one molecule of chlorine, it contains 2 atoms. So the answer is 2 mole. Do you understand? It's 2 mole. So this is what I would like to remind all of you here, right? Have a great start. How about 0? What about half mole? Half mole of ozone gas, which means how many mole of oxygen atoms? Tăng Trân hay? Half mole of ozone gas. What is mean by that? How many mole of oxygen atoms are there?
Yeah.
Now, one student suggested as 3/4. Is that, what do you think? Is it correct? 3/4 correct? Half mole of ozone gas means 3/4 moles of O, while somebody would say it as 2/3. 1.5. Three answers. What do you think? 3/4, 2/3, 1.5. Yes, yes. Why will you say that 3/4? It's 1.5.
Is 03 and divided by 2.
Yeah, that's right. It is O3. To start with, you need to get to know the gas. It is ozone, 臭氧. So the formula of it, it tells you something. You should know the formula. It is O3, and then for 1 mole of ozone gas, we have got 3 mole of oxygen atom. So it's just a simple multiplication. Here comes 3/2 mole of ozone. Of oxygen gas in half mole of ozone. Can you get the point? So it's not 3/4. Instead, it is just 3/2. Okay. What you need to do simply is to write the formula of the chemicals and count. Can you get my point? So half mole it is just a ratio. Tell me relative to 1 mole, how many are there? I just cut it into half, right? Originally, I mark it as 1 mole. Here comes 3. I cut it into half. Here comes 3/2. Understand? Understand? Okay. So this is what you should know about. The way of thought will be something like this. Okay, from today onwards. So, and what is that actually? If I'm going to ask you something more difficult, if I want to tell you how many are there, now instead of how many mole, now remember that 2 terms is different. How many or how many mole? Now it seems like number of pieces and and the dozen that we are going to tell, right? So remember, while you read the questions, you may see the conversion. If you have got 0.1 mole of water molecule, remember the times and that Avogadro constant. So be aware of the questions, the wordings. Okay, it's not just the chemical, but also the way to present the idea. Is it how many or how many number of moles? Of course, you know the conversion, you may find that the triangle, somebody may find it useful. So it will tell you when you are going to have a number of particles in a substance, simply it is equal to the number of moles times Avogadro's constant. Okay, if you want to, this is the way to tackle the whole thing. But if you want to get to know how many moles of the molecules of the substance it should be, is simply having a number divided by the Avogadro's constant, and you can get the answer. Do you understand the why it is presented in that triangle? Okay. Now, how about the third one? Is that I just want to know what is meant by 1 mole. Okay, so it's simply having the number of particles in the substance divided by the number of moles of it, and here comes so-called what is meant by 1 mole. It is what we call it as Avogadro's constant. Okay, can you get my point? So this is what that triangle works. Okay, if you still find it difficult, you may make an analogy by yourself by relating how many to number of pieces and how many moles as dozen, and you can do the conversion very similarly. Do you understand? So this is what you may know about today. And so number of moles, you may do it in reverse, right? It's just a division. So don't get too worried about that 2 equations. They are more or less the same. It's just a shifting of those numerator denominator in different places. in order to serve your own purpose. Questions? So we have got some examples. A sample contains 5.60 moles of sodium carbonate. How many? Now, some term is very strange to you. The first one is formula unit. And second one is iron, but not cation. But you have got two different things. Okay, formula unit, which means that the formula that is shown it on here, and trying to tell me how many are there. Okay, now it is somewhat very imaginary. Okay, somewhat we cannot just count it as a full. And if whenever you use it, you are now mainly deal with ionic compound. When you compare with molecules for covalent compound, for example, we simply tell how many molecules are there. Okay, but we cannot tell how many Na2CO3 molecules are there because this is not molecule. So we can do, if we try to minimize that times of embarrassment, I change the term a little bit, formula units. So how would you treat that? We have got 5.60, and you are going to find out how many. Can you see that? How many? So it's simply times the Avogadro's constant, and here comes a very big number. If I do it together with the ions, now the case is more complicated. Now, while you see this, you have to split the ions into cations and anions with the respective ratio. Now we have got 2 portions of sodium ion and 1 portion of carbonate ion to make it full. So in short, why is it times 3? Is that we have got 1 formula unit of Na2CO3, which means that we have got 3 ions in the substance Na2CO3. Can you get my point? So that's why we need to times 3. 2 for sodium ion and 1 for carbonate ion. So that's why the number will be quite large, larger than the A part. Is that clear? Now your turn to show me your thoughts. It is the class practice. Could you please do it now? Question 1. Calculate the number of molecules in 0.160 mole of carbon dioxide. Now, first of all, if you do that questions, you have to what? Circle the task. You're going to count the number. A second, number of what? Molecules. Molecules, not atom. Okay, so no need to make it complicated. In 0.160 mole of carbon dioxide. Okay, how will we deal with that? Wang Senghin. How many molecules are there? How many?
Uh, 9.632 times, and with check.
Yep. Okay. So what? Any unit for that? Any unit?
No unit.
No unit. Okay, because you are now having number. So that's right. So no need to think too much about the problem about CO2. So it is simply having a number of moles times Avogadro's constant. Okay, because you are having from dozen to pieces. Can you get my point? So if I want to make a dozen turn to pieces, you multiply it by 12. But you use the similar concept in mole. But if I say that 1 mole, which means 6.02 times 10 to the power 23. Okay, so you use the same concept and you will arrive the answer. So you may find this one, we times it as to represent mole, a very large number. Now, how about this number? Something I need to remind you is about the use of significant figures. We have got 3 significant figures in these calculations. Why? Now, because of the data, it will be given in 3 sig fig. And Avogadro's constant also in 3 sig fig. So, of course, you make a multiplication. The principle follows as the smallest significant figures wins, they will overlap. So it's still 3 sig fig. Both are 3 sig fig, of course, 3 sig fig. But if you see it as 0.16 mole only, okay, what is the number? What is the number? 0.16 only. So what is the answer I need to change? Do you know? If I say this 0.16, the answer should be what? Sorry. Now this is
9.6.
Just 9.6, of course, is wrong. The answer is 9.6 times 10 to the power 22, right? A very large number. Okay, so as said before, the smaller significant figures wins. They will dominate the overall accuracy of this data. Okay, is that clear? Now, question 2, the number of moles of nitric acid that contains 9.03 times 10 to the power 23 molecules. Okay, we try to do it in reverse, right? So what would be the answer? Lâm Thành Hon. Lâm Thành Hon, are you here?
Yes. That điểm 1.5 times
1.5. So the unit, what is the unit? 1.5 mole. Somebody you say 1.5 mole. You say 1.5. Which one is correct? What do you think?
1.5 molecule.
1.5 mole of molecules. Okay. So the answer, both of them should be wrong. Why? Because you have to check the significant figures. The answer is 1.50 mole. Why? As said before, you need to check for the significant figures. While you arrive at the answer, 3 sig fig, and the Avogadro's number is in 3 sig fig. So, but you press the calculator, they will only give you 1.5. Okay. So you should give me one more 0 here to denote that the accuracy it is in 3 sig fig. Do you understand? So this is what you have to tackle with that. Check for the significant figures. Is that clear? Now, how about question 3? Calculate the total number of atoms in 3.50 mole of ammonia. Now, just like the very first example I've just shown you, 黃振熙 are you here? Yep. Tell me your thoughts. instead of telling me yes. How would you arrive to the answer? Now, it seems that this one, you are going to have two steps, two important steps. One, you are going to spot about question total number of atoms, and then you try to say that ammonia. Okay, and the unit is mole. So you need to do two things. One, you make a conversion between ammonia and atoms. Okay, ammonia molecules and atoms, right? And second, you are going to convert mole to total number. Okay, the number. So that two concepts should be considered. Can you get my point? First question, how many for one ammonia molecule? How many atoms are there? One ammonia molecule contains how many atoms? Hello, Wang Junhei. Yes, that's 4, and then 4 atoms. Why? Because we've got one nitrogen and 3 hydrogen, right? But you can say that it is one molecule. As an entity, it's one molecule. But inside it, we've got 4 balls. 4 ball means 4 atoms. Can you get my point? So what will happen if I say that 1 mole of ammonia, they will contain how many mole of atoms? Yep, still 4. You can get what I mean. Okay, why? Because I just add the word mole here. Okay, no mole, I change it to mole. Say, how about, can you get the whole logic? How about 3.50 mole of ammonia molecules? How many moles of atoms are there? $14. How will you get it 14? 3.50 times 4 equals 14.0. Remember the significant figures. 14.0 moles of atoms. Now, the final questions. 3.50 mole of ammonia contains how many atoms? Can you see the tricky points here? Mole of atoms, I change it to atom. So it seems like what? Doesn't turn to pieces. Okay, you need to time something. So what should be the answer? Okay. Still 14. Now take a look on the term mole. And here comes just atom. Dozen. That's 1 dozen of hectares, which means 1 pieces of hectare. No. You need to time something. Time something. Times what? For dozen to pieces is times 12. But from mole to number, you need to times what? Avogadro's constants. Okay, so the answer is I would like to change it here, right? It is what? 14.0 mole times Avogadro's constant. So what is the answer for atom? 8.43. The answer is wrong, so little. There should be something more inside. .43 times 1. Once you will see the calculator, you may see the number. Just tell all those numbers inside.
8.43 and 10 to the power 24.
Yep. So the units.
Atoms.
Yep. You just say the atoms or simply no unit. Okay, because I just asked for a number. Okay. Is that clear? Now this is what I would like to show you, the way of thought. Now you may find it on your, that is what the textbook suggested you to answer. So which one would you prefer? Can you get my logical thought about that 4 steps? So the first step, first one step, it is we are now referring to the conversion of ammonia molecule to atom. So I just want you to get more aware of the factor times 4. Can you get my point? Second, for the second step, what I want to tell you is that if I want to project into bulk a large amount from a piece to a dozen, the same ratio still holds, which is times 4. Okay, can you get my point? So you may use the word mole, and the ratio is they are just still the same. Can you get my point? And 3.3, why do I say so? Because I just want to make you one mole as a unit, but I change a little bit about the exact number. I want this 3.50, and of course you keep this, and you still need to multiply by 4. So here comes 14.0 mole of atoms. Can you get my point? But sadly, you are going to ask for the number of atoms only. You need not tell how many dozens are there, how many moles are there. So what you need to do is to times that big number to make it as an atom, to make it a very, very large number. So here comes point number 4. Can you see my logical thought? Of course, you can set up yours by yourself, but the key is the clear logical step should be noted, and you should be aware of the formula of ammonia. Questions? Find it difficult or what? You find it difficult? Easy? No? Shall we move on? I'll give you 1 minute to see if you have any questions. 一問係唔識嘅、唔明嘅，要再講多次嘅，有冇？你覺得自己都 OK 嘅，跟到嘅，give me a thumbs up。thumbs up, thumbs up, thumbs up, not hands up, thumbs up, OK？ 唉，差唔多長學家鄧家傑、Ronald Lam、鄧俊熙。Or for those who find it very difficult, okay, you just put up a hand, let me know. 鄧家傑 do you feel okay, Ronald? 黃成軒 Hoàng Sang Hiên. Hoàng Sang Hiên. Are you here? First time? Slept? Yeah. Good. Nice.
Yes, sir.
Yeah.
我想問，但係點解佢隔離嗰邊係係8.44嘅？
8.44. Now you take a look on their calculations. Now which one is correct? 3.5 times 6.02 times 23. Power 23 here comes 2.107. Instead. And second, you decode that number and times 4. Tell me what would it be? It is 8.428 times 10 to the power 24. Can you see that? But because I want to make it in 3 sig fig, I change it to 8.43 times 10 to the power 24. That is the correct answer. Can you get my point? But not 8.44. But how come we have got a deviation? Do you realize? Because they use this data to do the multiplication. Okay, but this data is a little bit, we have done some approximation to it. So as a Chinese saying, 差之毫厘，謬之千里, and that will come to a slight difference. Can you see that? So what should I do in DSE? What should I do in DSE?
Use 5 decimal points.
Or somebody will say that you use 5 decimal points, but while you do the calculations, now while doing calculations is one thing, presenting an idea is another thing. Can you get my point? So if I were you, I would suggest I would do it like this way. While you present the data as each of the stop, you anyway need to make it as 3 sig fig, but hold the number inside your calculator. And then use that number in the calculator for further calculations. And here comes the most accurate data. And he will come to 8.43 times 10 to the power 24. Can you get my point? The way to present and the way you calculate, you are going to do it separately. And remember, no, you cannot leave your answer here as 5 sig fig. You cannot. Remember, doing the calculations in between the steps, you may use it, right, to keep your data, but the final data must not be 5 sig fig. Can you get my point? Because of accuracy, it is 3 sig fig and it is 3 sig fig. While the fourth significant figures and the fifth significant figures is meaningless, because of some variation inside, some error inside. Questions? Easy, difficult, or what? Now, easy start, right? How about unit? If you write it as number, if I ask for number, no unit. If I say that not total number of atoms, you may simply write no number or write it number atoms. It's also okay. But of course, according to English, if you say the total number of atoms, the most accurate saying should be no unit. But if the question asking for how many atoms are there, so of course you need to tell me how many with the unit. Can you get the point, Chaka? It's something about English, the way to present in English. If I say total number of atoms, no unit. If I say how many atoms are there, with unit. But in this case, even though for this question you mark it as atoms, I will not deduct your marks. Is that clear? Okay. So shall we move on? Any more questions? Now, but why do I need to have such idea? You may find it counting in chemistry is rather doesn't make sense. Why do I say so? Because actually, can you count? can you really count for me 8.44 times 10 to the power 24 atoms in 3.5 mole of ammonia? Can we really count? The answer is no. Do you know why? First of all, they are too small to be seen by you. Second, it is meaningless to count such a large amount of number. Can you get my point? And even though you die, until the day you die, you still cannot count it full. Can you get my point? So for chemists, we are so lazy. You need not count. Have you ever experienced any example in your daily life, which involves no counting, but you can estimate how many are there? Have you ever experienced anything like this? No? Lei Cheng, have you ever experienced something like this? If I buy certain units of something, you can estimate how many are there. I just need approximation. Yeah.
Maybe some soft drinks or some.
Sorry, somewhat.
Soft drinks.
Soft drinks. So can you elaborate more on that? How?
For example, one can maybe has 500 milliliters, and if you buy two, then that means that there's 1 liter of soft drink.
For this, you may simply ignore counting because the number is just 1 and 2, right? How about sesame? Have you ever been asked to buy some sesame seeds? Can you imagine the case you go to the wet market and go to the shopkeeper telling him, can I buy 100,000 sesame seeds for me? So what would the shopkeeper do?
佢話黐線咯，就係。
Oh yes, telling you are with that adjective, of course, with foul language. Okay, but in reality, they can still manage to do that. They can still manage to do that. For example, if I have a big bag of $1 coin, okay, one big bag of $1 coin. Of course, nowadays you have got a machine to count it one by one, to save your time. But in the past, people were very clever. That they tend to not count it. Instead, they use one method to estimate how many are there. Do you know how?
稱佢有幾重啊?
Yes, very good. How can we do that? Because I know something like weighing. You are going to weigh it, count it by weighing. Count by weighing. 原來我哋以前啲人咧稱嘢得㗎啦。Okay, so very often while you go to wet market, people would love to do that conversion. Can I buy some red beans? And so they instead of telling you how many red beans are there, indeed they have such ability. They would ask you to tell me how many mass do you want to buy. For example, 1 kg, 1斤咁樣咯，係嘛？ If they want to make it very, very seriously, they can really do so. It's by weighing, by counting. How? If I use $1 coin as an example, and you can get what I mean, $1 coin, and I need to weigh it and try to make it bulk. Of course, if the bag of it is too many, for example, 1,000 coins, there are as many as this. For $1 coin, you may think how many grams are there, and I project 1,000 coins and I can get what is that. But in the people, they are very lazy. They do not want to do such. For example, $1 coin, or maybe I try to make it as a $1 coin, and how many grams are there, and I use it for projection. I know that it is and it is 1,000 times, or even 50 $1 coin, and here comes what? The ratio becomes what? It's now 20 times more, and you can get a bag of coins. How many times are there? And you can project. Okay, you get my point. So try to imagine a case when you are having atoms, because it's too much to be seen. So chemists at that time, they are very careful that you use the similar logic to estimate by itself, by weighing how much content are there and what is the mass of it when you are having the reference number. So what is the reference number? It's by mole. It's by mole. So they were able to come up with the idea. We call memory about the relative atomic mass of carbon-12. It is 12.00000. Can you get my point? Atomic mass unit, which means that for the other relative atomic mass, they would have the ratio, okay, of a mass when you count it for compare with one carbon-12 atom. For example, helium-4 is relative atomic mass is 4.0, which means that it's just 1/3 of carbon-12 atom, the mass of that. So you may use that type of conversion to tell. If I know 1 mole of carbon-12 atoms, they will contain 12 grams of carbon-12. You use the similar logic. 1 mole of helium atoms, helium-4 atoms, they will contain 4.0 grams of helium-4. Can you get my point? So you can, so you may find there is something useful about RAM. Okay, now if I use the, if I change it to gram, if I change it to mole, that number, it is indeed molar mass. Okay, that number, we call that molar mass, which means that per mole of that substance, how many grams are there? Now, why do I need to use gram? Is because for the convenience of a scientist. You weigh it in chemistry lab, we always deal with gram only. Now, it's different from physics. We deal with kilogram in physics, but in chemistry, we deal with gram. Second, if you want to count the number in bulk, we'll use the word mole. So the unit will tell you something. It's our common practice. Gram per mole, we call it molar mass. Once again, I tell you what that is. It tells you the mass of 1 mole of the substance. Can you get my point? So why do I say so? Because different materials will have their own different molar mass. For example, carbon, we will weight it as 1 mole, we've got 12.0 grams. But for copper, you need to wait until it is 63.5 grams until you get 1 mole, such that you can get 1 mole. Why? 1 mole, but 1 carbon atom is heavier than 1 carbon atom. Okay? So if you use that type of conversion in mind, you can do something like this. Now, similar concept that you may know is from the shops selling buttons. Okay? 有啲賣樓嘅地方啊 you know it? It's not building. It's not building that in Chinese. We call it buttons, right? That button. So if you go to Nanchang Gai, for example, if you go there, they will sell you a bag of button. While the bag of button, they will have a constant unit. We call that one 一籮. Have you ever heard of that? What is mean by the law? Indeed, it tells you 10,000 buttons are there. Okay, can you get my point? So how can we count that 10,000 buttons? It's simply by weighing. Okay, but you know that different types of buttons, while you count it as 10,000, they would weigh differently. So what do they do is to get buttons of different style and mark their mass of it when you weight it as to represent 10,000. So the similar concept applies is the molar mass. Different materials, they will have their different molar mass. Aluminium is 27.0 gram. Iron is 55.8 gram. Simply speaking, I check the periodic table, I use the RAM, I change the unit to gram, and here comes the molar mass, gram per mole. Can you get my point? 唔同嘅物質有唔同輕重嘛，所以佢嘅 molar mass 亦都係唔一樣嘅。And it's not just molecules that you may count it as a molar mass, but also ionic compound. But the way to find is very similar. If for covalent compound, check its relative molecular mass. While for ionic compound, check its formula mass. Okay, again, ionic compound doesn't have any RMM. No relative molecular mass. I use formula mass. Simple. Okay. Simple arithmetic for 12.2. You can get what is that? I give you about 2 minutes. I'm sure you can do it. For methane, it is what? 16.0 gram per mole, right? How about potassium carbonate? And 138.2, ethanol 46.0, and finally for magnesium phosphate it is 262.9 gram per mole. One thing I would like to draw attention is the accuracy of the data. Now, because we are having just addition of data, can you see that? Addition of data. While 2 and 3, they are just the factor to multiply. How many are there, right? For convenience. So you may still count it as altogether 4 more plus, okay? Can you get my point? So if I'm going to deal with the accuracy of data, handling plus or minus, the accuracy of the data doesn't go with the significant figures. Instead, it goes with the decimal place. Do you know it? So you are going to check the decimal place. It is 1 dp. So the answer should be 1 dp. Can you get my point? So it is somewhat about mathematics. For plus or minus calculations, the accuracy goes with decimal place. But you are dealing with multiplication and division of data. You need to deal with sig fig. 有冇聽過啊？呢個黃耀朗有冇聽過呢個？
有。
加減數睇 DP 嘛，乘除就睇 sig fig 嘅，係嘛？有㗎嘛？係咪啊？真㗎？咁我唔講咁多咯喎呢個。So the conversion of the moles, mass, and molar mass, you can do such conversion. You can check the unit to help you arrive at the answer. Suppose you have got the mass of a substance, or divided by molar mass of a substance, which means per 1 mole how many grams are there, and you can project the number of moles of the substance. If I do it in reverse, you can. Okay, if I do it in reverse, for example, if I have the number of moles of substance, how many mass are there? Simply times it. Okay, and you can get the mass of a substance. Okay, so you make use of that triangle to follow your work. Your turn. Page 78. A reaction uses 214 grams of calcium nitrate. How many moles of calcium nitrate have been used? How many moles? So what you need to do is to have a formula. It's easy. It's what? Mass over molar mass, and you can project it as number of moles. Okay, can you get my point? So you use that formula and you can get the answer. It's 1.30 mole. Okay, to start with, molar mass of calcium nitrate is 164.1 gram per mole. I use it as a denominator. And you may find it 1.30 mole. Questions? For question 2, is somewhat mechanical. I don't want to spend too much time on that. I just show you the numerical answer. You may do it by yourself. One thing I would like to get you draw attention is that if you use the different materials, the molar mass can vary so much. For example, glucose, because one molecule of glucose, they are having altogether 24 different types of 24 atoms. 3 different types of atoms, 3 types of atoms, but 24 atoms per molecule. So the molar mass is quite large. Now you're having potassium dichromate, for example, an orange substance. So you may find that chlorine, oxygen, potassium is a chromium. We have got is quite heavy per atom. So they added to the mass of the molar mass of potassium dichromate. While for the mass, how will you calculate? Okay, you may use the other 2 data to help. You may project. So you may see that you'll be given, at least you need to give you 1 data, and you can get what you want. It must be either mass or a number of moles. For molar mass, don't worry. From the formula, you can know what is that. Okay, what I need is only 1 data from either mass or number of moles, and you can get the other one. Do you understand? So to conclude about today's lesson, I would like to give you the final task. It is on class practice 12.4. Okay, 12.4. What is that? You are given a sample of 94.2 grams of iron-free sulfate. How many formula units are there? How many ions are there? So what is that? You need to be aware of this iron-free sulfate. So what is the formula? Fe2SO4 and then 3. Only by having this, you can get what is that? And we have got 2 types of ions, iron 3 ion and sulfate ion with the ratio 2:3. Now, and what other information that you need to know? It will be the molar mass of iron 3 sulfate. Do you know? Which is a very large number, 399.9 gram per mole. Now, all those data should be enough for you to find out the answer. So your task is to find out how many what? Formula units, which means that unit. And how many ions? Now you need to consider this. The ratio, where 1 portion of iron-free sulfate, which means 5 ions are there. So the multiplication factor is 5. Is that clear? Is that clear? Now go home and please finish question 1 and question 2. Now shall we have a slight conclusion of today's experiment of today's lesson? Is that we have come up with 2 chemical equation, mathematical expression. One to relate number of moles. So if you can really count, so you can have the number of the particles over Avogadro's constant, and you can get number of moles. And that is the theoretically work, because you can really cannot count. I can just estimate, but for this one on the right hand side is far commonly found in our daily life. You count it by what? Weighing. You count it by weighing. So here comes another equation, which is what? Mass over molar mass. So today, here comes we have got two formula. The first one and the second one. What do you think? Okay, this is what you know about today's lecture. Questions? Just tell me your level of understanding such that I can adjust my pace. Am I speaking too fast? No. From morning longs 9, you may find that I'm now teaching too slow to you, right? Isn't it? You want to make it fast? 6 9 7 4 7 8 8 6 7 7 7 5 8.5 5 6 6 7. Okay, not bad. Level 4. You may take some more time on it. I would like to give you the archive on the YouTube very soon, such that you can retrieve and try it out by yourself, bit by bit. And could you please finish practice 12.4 before we meet next lesson? Now, and somewhat about the tutorial, I may find that for calculations part, it may be very rushed, and I would like to have some other backup measures for the people who want to calculate more slowly, and I would like to schedule it on Monday afternoon, very similar to our supplementary lesson time slot. I just want to see if anyone would like to join it. Okay, if so, I would like to have it next Monday. Okay, tell me in our WhatsApp. Okay, tell me in WhatsApp. Any questions? If not, see you guys. Bye bye.